develop an equation for any random location once this falls from the top downward to give me an expression for what the angular velocity was, right? All right, several students asking already. So this is kind of what, the way I would have done it. I don't know. You might have done it differently. This is the way it appeared easiest to me. I call this spot right here at the pivot 0. Okay? So it starts in this position right here at this height. So the original height is L over 2. You remember from last time it had a length of L and a mass of M, right? And it was a uniform bar so that center of mass was in the center. Okay? So if I do that, it starts off at rest and then it starts to fall. It starts off at rest, has only gravitational potential energy. Okay? I called this spot 0 simply because it seemed easiest to me. And I didn't know where it was going to end up anyway. I didn't know if it was going to be in here, 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 or here. So that's just what I decided. So when it's at any other random spot, like right here, then it'll have rotational kinetic energy and it'll have potential energy. Now my potential energy is going to end up being negative at this spot, but I don't care. It's just below the 0 point, okay? And I defined the angle theta to be from here to here. And then what I did was say, look, when it's in this position here, my potential energy should read 0. And when it's in this downward position, my potential energy should read mgh, where h is L over 2, but it's below the 0 point, right? So I used cosine to help me do that, okay? Because like when it's in this position here, when I have mgh, I define h then to be mg L over 2 cosine theta. Okay, because in that position it's an angle of 90. Cosine of 90 is 0, so that comes out okay. So when I get down to this bottom position right here, I should have an mgh that equals mg, once again, L over 2 cosine theta. The angle from here to here is 180, right? So cosine of 180 is -1, which gives me what I should have down here, mg L over 2, but that's negative height, right? So I should get that. So it looks like this is going to come out correct, all right? So then all I have to do is solve it for omega. My moment of inertia is 1/3 ml squared since it was a uniform bar. I just have to solve for omega. So all the really hard physics is done. The rest is just algebra, right? So once you get past this point, it's just math. So do you want to see what the final answer is?
Sure.
Or do you care?
I'd rather just have you say for grade.
Can we turn it in?
Sure. Turn it in. Okay. We have one last major thing to talk about with rotational kinetic energy, something we haven't seen yet. So here we go. We're going to have a race. Our race is, we got an incline here. And at the top of the incline, we're going to put things that roll. All right? Things that roll. Things that roll would be things like a hoop or a disc or a human.
Body bag.
Whoa! A solid sphere and a basketball. Here. Instead of a solid sphere, let's do a marble. L-E-E-L. Marbly, Marbell.
It's a marbly.
Marbly.
That's right.
All right. I wrote EL at first. I'm like, that doesn't look right. All right, here we go. So we have a hoop, a disc, a marble, and a basketball. All right, I need you to talk amongst yourselves. I need you to decide which one shall win. I need you to place them in order of fastest to slowest down the incline-y thing.
Is there friction?
Of course. Oh,
Anastasia.
thank you, Anastasia. Race number 1 is frictionless. Race number 2, friction-full.
Basketball gonna lose on the friction full one because it has those little ridges on it.
What way?
All right.
What's the friction of the
First race, there's no friction.
I think whoever wins the first race just
Here, we'll add one more contestant then.
don't.
Ruin.
Do they all have the same radius?
We'll add a box.
And lose.
Actually, we'll make it a cube, a cuboid.
They all have the same radius?
A three-dimensional object on a two-dimensional
No. Well, okay, we'll make it easy. Let's say that all have the same mass m. Mass equals m. Radius equals radius.
What about the radius?
And the box.
These are very heavy marbles.
Well, wait a minute. Let's do it this way then. This would be 2r, so the box is the same size. All right. All have the same radius except for the box, which has a length on its side of 2r, so they're all the same size. They all have the same mass. So we have two races. A race where it's frictionless. This is our frictionless race right here. Our coefficient of friction is 0. And then we have our race that has friction. Okay? Okay, so let's talk about the frictionless race first.
Okay.
What was the question again?
Conservation.
The question is what is your favorite color?
Green.
Blue.
No,
It's
we're yellow.
No, it's green. It's green.
You're gonna still get wrong. It's
Which one has the highest
Which
velocity?
one
like-
will
I
reach
like
the bottom
wavelength.
first?
998.
It's a race.
Oh, there's no friction. They all get done at the same time.
Okay, let's say it again.
What's your answer to that?
They all get done at the same time.
All right, if there's no friction,
Not music, but art.
if there's no friction, they never start to roll. None of them.
They just slide.
They all slide down. Since there's no friction, they all have the same mass, they all have the same incline, they all have the exact same free body diagram, whatever the object is.
Therefore-
Here.
None of them.
Here you go. Here's the free body diagram of all of them. There's an mg, and there's a normal force, and mg sine theta equals ma down the incline in this direction. M cancels, so their acceleration will all be g sine theta. They'll all reach the bottom at the exact same time. Yay, team. All right, now, what if there's friction?
Then life
No
gets
row.
Life gets a little more complicated. So first off, once there's friction, the box probably doesn't stand a chance, right?
Yeah,
Or does it?
of course not. It'll roll.
Let's just see. It'll roll.
Yeah.
It has its whole surface.
Okay, here's the box. Here's any of the spheroid objects.
Spheroid.
Circuloid.
Of a plane, and then it wins automatically.
But look, if there's friction, draw the free body diagram for both of these.
Yes.
Denying you the opportunity to choose your method, I've chosen forces for you. I've chosen dynamics as a way to look at this problem. Okay? We're going to look at this also in terms of energy. We're going to see how they tell you two different things, but that they mesh together. Okay? All right, so we're looking at this from the standpoint of dynamics first. I've asked you to draw a free body diagram, but you could have looked at this in terms of energy strictly, and you would have ended up with the same idea or answer. Okay? All right, our free body diagram right here looks like this. We have, from our center of mass, we have an mg on both. On both of them, we have a normal force. Now, our normal force Over here goes like this. Technically it comes from the surface. Okay, now over here, we have an object that's going to rotate, right? So it's dreadfully important that we draw all of our forces exactly where they're applied, because we're going to have torque again, right? And in torque it makes a difference. In this object that's not going to rotate, it doesn't really matter where I draw the forces, really. Okay, over here, where's the normal force? Right here, right? There's our normal force, or F sub n. Okay? From the point of contact. All right, where is our friction force? All along here, force friction. And right here, it's going to be right along here, force friction. Now, what kind of friction are we going to have on this one? If it moves at all, it's going to be kinetic, right? Okay, this one over here is going to be, assuming it doesn't slide, right? We're going to have static friction over here. So we don't know a whole lot about this box at the moment. It could be sliding. It could be static, right? If it's not at a high enough angle, it may just be stuck there. All right? So force friction, we don't know. That is a big question mark. Okay? All right. Now, taking a look at this thing right here. Okay? What does dynamics tell us? Okay? Do we, first of all, remember we always draw a free body diagram. Next thing we always ask is it accelerating?
Yes.
Which way? Down the incline. So, if it's accelerating that way, how do we set up our coordinate system? That way, right? To make life simpler on ourselves. So our coordinate system will look like thus. A parallel and perpendicular coordinate system. And so when we have that, then whether we need to or not, a lot of times it's just best to write our F equals ma. So F equals ma in the parallel direction. What do we get? Everybody write that for me. Same methods we always use.
It is mg sine theta minus mu normal force friction
We have an mg sine theta right here minus force friction static equals ma.
force normal.
Okay? That's what we get there. Now I'm boxing that up. Because can we do better than that?
Yes.
Not really, unless you're told it's at a maximum.
Okay, that's static, right?
Unless, like, if you're told it's a maximum.
Well, you can put
Oh, here's our danger point, right? Remember that static friction is, force of friction static is less than or equal to mu force normal. So once we have that less than or equal to, unless we know we're at the maximum value, then we're stuck. That's it. We can't do any more.
We're stuck.
Oh my.
She said later.
That's it. We can't do any more because this is the dangerous one. It's that lazy force that only does what's necessary. So we really don't know what that value is, do we?
no.
All right, so let's quit. Stop. Sum of the forces equals ma in the perpendicular direction. Does that tell us anything?
Well, it tells you that
It's not really
normal.
Yeah, hopefully it's not being thrown that way or called.
Normal equals mg cosine.
Okay, it tells us that, which may or may not do us any good. We don't know. Okay?
Some torque.
All right, yeah, so I think it's time to do some torque. Because we got nothing else at the moment, right? That's as far as we can go. We're stuck since we can't put mu force normal in here. We normally would plug that back in, but we can't do it this time. All right, so let's try the torque.
We tested.
Can we test this little experiment? Maybe. I think we have some equipment for that. All right, so here we go. Torque.
That's
Friction
sum of forces
causes
times
torque.
Okay, where are we going to draw our torque thing about? About what point?
From the pivot.
We could do the pivot point, right? Now remember from last time, we talked about when we have something that's moving, okay? We have two options. No, we talked about kinetic energy. Back up. I'm confusing my talks.
Yes.
All right. You could pick this pivot point here. If you pick that pivot point, then what's your torque going to be from? mg, right?
Yeah.
And it's going to be at an angle. And we have to find out the moment of inertia about this point. Is there an easier way? Can we pick an easier point?
Center mass.
How about we do center of mass? If we do torque about the center of mass, okay? Because it's actually spinning about its center of mass, right? As it rolls down, it's just the center of mass is also moving, right? All right.
That's what we know the motor is for.
Yeah. And plus we know the moment of inertia about that point, right? So what's the torque about this point right here?
It's yeah, the radius times
How many of these forces cause torque?
one.
Oh, wait, this is more friction.
Just friction. Because the normal force and mg pass through the pivot point, right? So it's just force friction. But wait a minute, how did I tell you always to do torque?
R.
Radius first,
Force friction.
then the force, friction, static,
Cosine.
and then cosine theta, but our cosine theta is going to be, no wait a minute,
One. Cosine theta will be 1.
it's sine theta, right?
Okay.
It's a cross product, right? Sine theta, what's our theta? 90. Sine of 90 is 1. Alright. Sine theta, but that's 1. Equals our moment of inertia times alpha. Is there anything we can do with this? Now we don't know which one of these that we have just yet. Is there anything else we can do with this?
A
A
alpha.
over R.
Hey, alpha is A over R, right? So R, F, sine, no. F static equals I, A over R. Yes, I am.
IG sin theta.
Can we now find the acceleration of the object?
Yes.
How?
Substitute force. Friction.
Is this
Yeah, because I can rearrange this. Notice I have force of friction here, which is the same force of friction I have over here, right? So I have mg sine theta minus force friction. Force friction is going to be
IA.
I, A,
R. Force friction.
over R squared?
A over R squared.
Where's that?
Force friction.
So I move this to the other side.
I
I know. You want to
Sometimes
cancel
I
it
just-
out.
Yeah.
Want to cancel it out because it usually cancels out. All right, and that equals MA.
And
All right.
And my change.
Let's solve for A.
Let's move the IA over squared to the other side. Back up.
Solve for A. We get A equals mg sine theta over m plus I over R squared.
So as I increases, A decreases.
Yeah, so my question is, does that tell you which one reaches the bottom first?
Yes.
That one?
Which one reaches the bottom first?
With the one with the smallest.
That one.
Okay, if you want the largest possible acceleration, you want the smallest possible I, moment of inertia. Okay, so, you've memorized these by now, right? So we'll start here. Marble. What's the moment of inertia? 2/5 mr squared. Okay, what about a disk?
1/2.
1/2 mr squared. Okay, what about the basketball?
2/3.
2/3 mr squared. And this one, of course, is just mr squared. So do you see that since they have different moment of inertia, they'll reach the bottom at different times?
Yes.
Okay?
So, Mr. Baron, can you define a moment of inertia for like any object?
Yes.
So, like a box, even.
Yes. You sure can.
He's like,
But it won't be of any use to you unless it's going to actually be rotating. But, like for instance, if you have a large object and you're going to tip it over, like say here. Then we have this object and I'm going to tip it over, then yes, its moment of inertia would make a difference about that pivot point as to how, when its angular acceleration is going back.
You had to stand the box up instead of having it lie down on the side.
Well,
if it's a box, it'll all be
actually
the
it would be a
same.
really complicated problem. I mean,
Like if you have a steep enough angle.
if you have a
the box
steep enough
roll.
angle, the box would rotate. Now here's the
And then
deal.
it slides.
If you have a box like this, it won't rotate until you get to a very steep angle. But the key thing is this. So you have a box like this. This box would rotate because the center of mass is outside. I mean, yeah, the mg will pull outside of the pivot point end of the box, and so that one will tip over. So that's the key. Once that mg passes outside the limit of the pivot point, then it will start to rotate. So you could get something to do that. But then the problem is that as it tumbles down, it's a time-dependent problem where the moment of inertia actually changes because, like, it has a certain pivot point here. We'll see. I guess the moment of inertia will stay the same. Yeah, because the pivot point here, 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 and here will give you all the same moment of inertia. But you could have an object that was not uniform, and then the moment of inertia will change as it hits these different pivot points,
No.
and it's quite complicated.
Once it tips over once, doesn't it just like...
Now this one, as this one tips over, it'll hit and stop, right?
Yeah.
No.
Then you change it, it just slides.
Yeah, then it'll slide. All right. So here you go. There's the acceleration. If we want to know the velocity at the bottom, how do we find the velocity at the bottom then?
Energy.
We'd have to use kinematics, and we'd need more information. We would need the information of how far this is, what kind of length we're talking about, right?
Or like how, if you have the angle, just the height.
Yeah, or if you have the height, that's true. That's correct. If you have the height and the angle, it's the same thing. You just need that distance it's traveling through. Okay? All right, so here we have some things. Here, let's get
Physics in action.
Dun, dun.
Physics should have a speech.
Dun, 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 dun.
all right, let's try this.
I'm rooting for
The block.
You ready for the box?
the underdog.
You rooting for the underdog? All right, let's see if we can do this up here without killing anything.
It would be 3 years.
Get my software out of the way. All right, we need to set them up on something. How about this? I have to spill that. Here we go. Here's the other one.
Go, Boxy!
Okay. So, which one will win?
Drag racing.
Same mass, same radius?
I think that this is gonna be
What does our physics say should win?
the smaller eye.
We want the smaller moment of inertia should win, right? All right, so here we go. All right, it's your job is to not let them kill anyone. All right. Now, let's try that again, but let's try
These are
with...
the same mass.
Yeah, these are actually the same mass.
That's what I was thinking.
That's cool.
They are the same mass and the same radius. All right, so now this has a different radius and a different mass. Now, according to this, have different masses, right?
Yeah.
Hmm.
But the radius is much smaller.
There's a smaller mass and a smaller radius,
That
right?
increases the radius is squared.
Hmm. Do you have a guess on which one will win?
I say the top.
I'd say the
That's
bottom. Well, I don't know how
No, I
heavy-
think the disc.
I don't know how heavy they are.
Yeah.
Okay, I'm trying to put them that they're at the same center of mass location. Ready, set, go. Ooh, that was a pretty close one, wasn't it?
Yeah, I don't think
That one's
I thought it was a disc.
We have a non-uniform pinky ball. High bounce pinky. Well, that surprised me. I thought that pinky would win. Let's try it again. Ready, set, go.
Oh, it did win.
Pinky,
Try it again.
no, Pinky ran into the
Pinky's having
disc.
trouble.
Here, let me put them at the same starting location
backspin.
and see if that makes a difference. Ready, set, go.
So,
Pinky win? All right, I think Pinky should win. All right? I believe Pinky should win. Let's just see. All right? Let's take right here, and let's see, the acceleration is mg sine theta over m plus I over r squared. Okay? All right, now, let's put in Pinky, which is this one, and let's put in the disk, which is this one, and see which one should win. All right? If I put in Pinky, then I get mg sine theta over m plus 2/5 mr squared over r squared. Now look what happens. The r squareds cancel, and the m's go away.
So it's 5
Oh,
halves.
So we get, now there's a 1 out front here, right? So you get a
5
g
sevenths.
sine theta over a
7/5.
7/5, which is
5
5/7, right? Okay, that's Pinky's acceleration. All right, notice that the mass of Pinky and the radius of Pinky didn't matter. Okay? So now let's do that with the disk. The disk, we get mg sine theta over m plus 1/2 mr squared over r squared. Again, the r squareds and the m's all go away, and I'm left with a 1 2/3 or, no.
That's 3.
This is 3/2, and then flip it over, it's 2/3. So you get an acceleration of 2/3 g sine theta.
So I
Okay.
can have a giant disc and it'll lose to a marble.
That's correct. A giant disk should lose to a marble.
That's mean.
Now, because the friction should disappear, right? And the mass and the radius should
That
disappear.
would be one big marble.
Now, tell me, everybody, what is 5/7? Mathematically, what's a decimal form? And what's 2/3? 2/3 is 0.67.
0.714.
And this is 0.71.
Yeah.
Now, is that what we experienced? That they were very close.
Yes.
They were very close. Pinky won only by a little bit, right?
So the marble will only edge out the.
Yes. So the marble will only edge out the giant disc. If the track is not long enough, you won't notice the difference.
So when it's long enough, you'll see the difference.
Yeah, when it's long enough, the acceleration over enough time, you'll be able to see the separation, right?
Yeah.
Okay, so we got what we expected, that this one wins, but only by a little, right? Okay, now when we looked at this in terms of forces, notice that this is rather long and involved, right? But it does work out. But what we had to do is figure out the forces in the parallel direction. Turns out our forces in the perpendicular direction, while this equation is great, it just didn't help us this time. Okay? So there's nothing wrong with it, it just didn't help us. We go over here and figure out our torque about the center of mass, and this is the one that helps us put the friction up in here so that we can find the acceleration. Okay? And we find that in a race, here's our winner. This is the winner, number 1. Our second would be this one. Our third is this one. Our fourth is the poor hoop. The hoop gets its butt kicked every time. And well, except for the box, right? The box is an incomplete. It never really entered the race when we roll. Okay?
Disqualified?
Yeah, the box actually, I guess it either never runs or it will slide. But since it slides with kinetic friction on it, it's going to lose. Yeah.
How do they figure out the angle and the time period when the box itself begins to rotate?
Now, we talked about that real briefly amongst ourselves up here, but you can actually figure a moment of inertia on the box about its pivot point. And it will rotate if the... In fact, who knows, they could give you this problem. They could ask you this question: at what angle will this box start to rotate? And the key thing is that whenever this mg passes by this pivot point, then it'll start to rotate. So whenever you get the box high enough up, here, can we do it? Now this will probably start to slide before it'll rotate. Okay? But it won't start to rotate until we get the center of mass past this pivot point.
Do you have like a rough?
It won't rotate. It'll slide instead, probably. It's easier.
Rotate it at the end.
It did at the end, yeah.
Do you have like a like a back mat?
Yeah, if we had something sticky on here, like a sandpaper, then we could get it to rotate.
Like the friction and the friction has to be a lot higher.
Exactly.
Put a little piece of tape.
What about
Put a
that
pin
box?
or something.
This
Trips
one?
over your thing.
No, the box.
It's all bruised up.
All right.
Happy lunch.
So, Mr. Bruin, if that's true, why are we running around on spears instead of tires?
Why aren't we running around on spears instead of tires? Good point.
Oh, those look right there? Yeah.
All right.
That's why you gotta be an
Um,
engineer.
Now,
It's like you couldn't.
you are right that a sphere, a solid sphere,
You'd have to be
would be easier for you to get rolling. That's correct. The problem is that its contact area with the ground will be smaller than a flat disc, so you'll have less sideways control and
You can't turn.
yeah. So you
Well, but if you're on a disc, can't you just move your car?
Oh yeah.
If you're on a
Like a
sphere,
remote control.
well, that's true. Well,
But then your momentum would be too.
I mean, you could roll like this. Yeah, but if you have an axle, no.
It's a hover around.
I guess you could turn your axle like
have
this.
you seen those vacuums that are based on that?
Oh yeah,
Yes.
that's really cool.
They do have some things like that where they have a sphere wheel essentially that you can roll it in any direction.
Yeah.
The other thing is if you have a solid sphere, it will be a very bumpy ride. The reason originally tires were
That's
solid,
why.
and the solid connection between you and the road is very filling, knocking out
Unless you have
of
perfect
your
roads,
mouth, bumpy.
we're not going to go with you.
It's very jarring in an environment like that. So what they do is they fill the tires up with air to make them springy. Okay, you could. So it would be a worse ride with a solid tire.
That's why they tell us not to reinvent the tires.
Wait, why couldn't they have all the sphere tires?
All right, here's the deal. Now let's look at this same thing, but in terms of energy instead. Okay? All right, so a rolling object, in terms of energy, what kind of energy do we begin with?
Gravitational potential.
Gravitational.
Okay. First of all, is it okay if I say this? Are there any non-conservative forces?
Because we don't have friction.
We do have friction.
In the first case,
Yeah, that's right.
No, no, no. Even if we have a rolling object, we have friction, right?
Yeah.
yes.
But it's static.
Okay, back up. All right, back.
But it turns into kinetic.
Okay, let's say that there is no friction. If friction equals 0, then can we say this?
Yeah.
Yes.
Yes, and we would say that mgh at the top equals 1/2 mv squared at the bottom. And would there be any rotational anything?
No.
So this would be the same for all of these, including the box, and so they all end up at the bottom of the incline at the same speed.
Yes.
Everybody okay with that?
Yep.
All right, now let's say that there is friction. So mu equals yes. Now we have friction. Now, friction is a non-conservative force. So can we still use conservation of energy?
I want to say
Yeah.
yes,
But
but no.
it's gonna be different.
And I want to say yes as well. Can somebody explain why, even though we have friction, when we have a rolling object, we don't have to worry about it? Yeah, because it's static friction, and static friction, work is a force that acts through a distance, right, or displacement. Since the static friction is not displacing the object, only making it rotate, there's no work done by static friction, so no frictional losses, so we still have conservation of energy. So now this time at the top, we have gravitational potential. At the bottom, what do we have? We have kinetic, but we have two types now.
But I don't care.
We have translational plus rotational. Now, very important, everybody. Translational plus rotational. So we end up with mgh equals 1/2 mv squared plus 1/2 I omega squared.
At the center.
And that is correct. We are talking about the motion of the center of mass. Thank you, thank you, thank you. We need to, I forgot about that. We need to make sure that we designate what point we're talking about, right? All right, so there we go. Remember last time we said that if we have a rotational point that's not moving, then we could just say it's all rotational kinetic energy about that pivot point and no translational, right? But since this object is translating, it's just easier most of the time to say we have translational kinetic energy of the center of mass, and we have rotational kinetic energy about the center of mass. Okay? These two have to be about the same exact point, or otherwise we're doomed. Okay? All right, so here we go. Does everyone see that if this gets bigger, the velocity gets smaller?
Yeah.
If the moment of inertia gets larger, the velocity at the bottom has to be less because I only start off with so much energy. I start off with this bucket of energy. Afterwards, I have the same bucket of energy, and it can be split between these two types. If the moment of inertia is large, then we'll have more rotational kinetic energy than if the rotational kinetic energy, if the moment of inertia is smaller. Does everybody see that? Okay. So, once again, we show that the marble wins and that the hoop loses. The hoop loses by a long shot. Okay? All right, and so we can calculate the velocity at the bottom directly from this. We cannot get the acceleration that easy from this unless... How can we get acceleration doing this?
Kinetics, or kinematics.
Yeah, we have initial velocity equals 0. This gives us our final velocity at the bottom. And then if we know the distance, we can use that v squared equals v naught squared plus 2ad, right? 2ax minus x naught. So we can find the acceleration backwards from kinematics. So that's possible as well. So we can find the same two things with forces and with energy using kinematics in both cases. All right? There you go. And we're done.
So say we want to know at some other instant in time, we would have to put add MGH on that time.
I love thinking weird.
Okay, good point. Everybody?
Because that's just at the bottom, right?
Yes, this is for at the bottom. Now, remember, they might not give you this height, so you might have to find the height, blah, blah, blah. They try to make it hard on you. But if you wanted to know what was going on right here, then you could do one of two things. You could put potential energy over here, keep the same zero height, or you could just move your zero height up to here. and then redo it, and it ends up the same thing.
Could you make that like one half?
Yes, what you could do is you could call this, you know, if this is at 1/2, make this 1/2 h, essentially make this 0 location, so you have no potential at the end. It ends up mathematically being exactly the same. Now, in a problem, they will probably tell you where the 0 point is if they're asking. If they need to know what the total energy is at some spot, they'll have to tell you where the 0 point is. So they'll give you one maybe. But if they just ask you the velocity at the bottom, you can pick the height wherever you want it to be. Okay. All right, number 8. Number 8. What did you say? It looks creepy?
Yes, exact word.
Creepy. Wow, I haven't heard that since Halloween.
It's so long.
It's been so long ago. Okay, we got this. And this. And this. And this contraptionated thing.
Can I use that?
Alright?
Yeah.
But it's unreliable.
Alright, looks like my object here is not going to rotate very good, but hey.
Oh, what the hell is it?
Alright, you got a car being held in place by an unreliable winch.
Yes.
The gearbox of the winch breaks at the moment the car drum system at that moment the car drum system free falls from rest, shown in the figure. During the car's fall, there is no slippage between the massless ropes, thank you very much, and the pulley and the winch. Find the speed of the car when it hits the ground. Okay, piece of cake. Okay, now,
It flies into.
you could, yeah. And you want to know what the speed is right here. So velocity right here. Now, what kind of problem does this look like? Could be kinematics, trying to find velocity. But if you're going to find velocity, you need to know acceleration using kinematics. So you'd have to use forces. And you'd have to break this thing into, oh no, several free body diagrams, right? You have a free body diagram for this one, a free body diagram for this one, free body diagram for this one.
Oh, there's 2 pulleys.
There's 2 pulleys, both with mass.
Oh, yeah.
Yes. All right. So, and by the way, did they give us the mass of the pulleys?
They gave us a moment of inertia.
Okay, well that'd be okay, right? They gave us a moment of inertia, so we could figure out torque equals I alpha for this one, torque equals I alpha for this one, and then F equals ma for this one. Find the acceleration of everything. And then, do we know the height it falls from?
Yeah.
Yes, they do.
I'm afraid. Why is the pulley?
Because I'm afraid.
Why is
Mine says 2. 2 what?
Mine says 9.
Mine says-
Height of 2. I guess that's 2 meters.
2 centimeters.
2 miles.
Yeah, there's no units. Baddie homework.
What
No
is
units.
Mr. Bruin,
What does it say when you work it out?
It just says 2.
I would say, well, because the radius is 64 centimeters, so.
I'm hoping that it's meters because it looks like they just punched that number straight in. Yeah.
why is the picture 37 centimeters and then like
I know, it's not to scale.
Because you work it out.
All right. Hey, who wants to work this with forces? Raise your hand.
Thing is,
Okay, whenever it looks complicated, always ask yourself, could I solve this with energy? Because that might save me a lot of effort.
Okay, let's solve it with energy.
All right, let's try and solve this with energy. What kind of energy do we start with?
Gravitational potential.
First of all, can we say this?
Yeah.
Is there any friction messing us up?
No.
All right, so what kind of energy we start with?
Gravitational.
mgh for this. Now, notice these other pulleys have, yeah, they have gravitational potential energy, but it's not changing, right? Okay, we're going to call this height equals 0. Is everybody okay with that?
yes. Very nice.
Okay, when we get to the bottom, what kind of energy do we have?
2 rotationals.
We have k rotational for the big one, plus k rotational for the small one, plus k translational for our poor little car in our problem. I should have drawn a car here because it's being held up. This is one heck of a device to hold us up there.
Yeah.
That would be actually kind of fun if it didn't break.
Is
Should be a ride.
All right, there you go.
You can go in there first.
Now, please be aware, we have a 1/2 I omega squared here, plus a 1/2 I omega squared here, plus a 1/2 mv squared. This is for car, this is for little, and this is for big pulley. Now, when we transfer omega to v, please be careful,
Different radius.
different radii.
Radii. Yeah.
Right?
yes.
Now, if they had given us that these were like disks and we put in like 1/2 mr squared from up here, then the radii would cancel out and it would be no big deal, right? But they give us the actual moment of inertia, a number to plop in here and here. So our radius that we put in here for our omega, remember that's v over r, v squared over r squared. That radius is important. Make sure you get the right one. All right, hey, that's energy. That looks really simple.
That's more.
Not frightening at all. That we've covered forces, and it's the rotational inertia stuff, or the rotational dynamics that kind of gave y'all fits last time. Okay? So please make sure that you review that. Remember that the new stuff on this test, shh, please, write down. Remember that the new stuff on this test includes, we have work equals change in energy, we have power, we have conservation of energy, and remember that we had a new thing, which was potential energy functions, right?
Yeah.
So don't forget potential energy functions. I guarantee you it shows up on the exam. All right? So,
The graph.
yeah, all that graph stuff, and also that, the work done by a conservative force equals the negative change in potential energy,
I know it's easy.
right? Or that the force function itself is equal to negative derivative of the potential energy function. Want me to write that on the board?
Yes.
Okay, here we go. Remember we had this stuff, that the work done by a conservative force,
Like the
F dot dx equals the negative change in potential energy. Okay? And we also said that the potential energy function, oh no, this is the potential energy function up here already. That the force, the conservative force, is equal to the negative du dx of the potential energy function, assuming it's an x function. Okay? And then we got these two graphs, right? Potential energy versus x, and force versus x. If my force function looks like this, I'm just going to make one up. If that's my force function, what does my potential energy function look like? Or is it easier to do the other way around? No, that's going to be too hard because you have to integrate this to get that, right?
Yes.
Pretend they're.
They probably won't give you it that way. They'll probably give it to you this way.
Okay, it starts at like negative something. Yes, we call
Negative
it
6.
negative 6.
Because it's a negative slope.
Or it's a positive slope.
Positive slope, so you have the negative of it. Negative of the slope, sorry. So it goes like this, and then it goes up to 0. So you have 0 slope, and then it goes up to this side. If I do it right, these my transition's off. Okay? So is that thing stable? Is there an equilibrium point?
Yes.
Oh yes, we're the
From here to here, right? It's an
Yeah.
equilibrium. This is neutral stability here, right?
Yes.
Because if you just place it, it should stay. I mean, it just, well, it'll stay wherever you place it, right? Okay, to have stability, to have a stability point, you have to have a potential energy function that looks like this. That's a stability point, right? Equilibrium here, equilibrium here, equilibrium here, wherever the slope is 0.
there's only stability on the.
This is a stable equilibrium, an unstable equilibrium, and a neutral stability. Okay?
But what do you mean neutral?
Neutral means you could take it, place it somewhere else, and it would stay put.
Okay, but if it goes farther than that, it'll.
Yeah, it's only stable from here, neutral stable from here to here. So technically, I guess, if you gave this a push, you could argue that it's unstable because it would eventually go away,
So,
right?
Mr. Byrne, but if it started at 0, it would go to there, and then it would continue, right?
If it started at here,
Or, yeah. Or no. Understand.
if it started here, it would move this way. Because the force pushes it to the left.
Yes.
Okay? Oh, a large sphere rolls without slipping across a horizontal surface. The sphere has a constant translational speed of 10 meters per second. The mass is 25 kilograms. The radius is 0.2 meters. All right, everybody put up your e-homework. The moment of inertia of the sphere about its center of mass is 2/5 mr squared. So we got this. Moving this way at, 10. Rolling this way. Moment of inertia is 2/5 mr squared.
Well, I is 2.
Yeah. It's an incline.
It's a
Incline of
solid
25 degrees. Okay? Height of the incline is 3 meters. All right. It rolls as shown, rolls up the incline without slipping, ding, 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 without slipping. All right, part A, calculate the total kinetic energy of the sphere. Should be, everyone do that for me, please. You should end up with a number.
Is it?
Pretty good.
Wait.
Yeah, 1750.
Yeah, 1/2 mv squared plus 1/2 I omega squared. Plug in, crank out, and you get 1750 joules. Nice.
Are you plugging in like
The only thing that's important right here to plug in for sure is that you get v squared over r squared needs to be plugged in here. And you need to plug this in right here, in here. Otherwise, it's just plugging in numbers. So those are the two transformations you got to put in there.
But don't they give you the I as
Not as a number.
Yeah, you have to calculate it out.
yeah, okay.
But the
All right.
R squared cancel.
Yeah, the r squareds cancel, so you end up with a 1/2 mv squared here, and then a
Times 1 plus 2/5.
2/5.
Like if you can take out 1/2 mv squared for both things.
Oh yeah, this is the 1/2 mv squared. This would end, if you leave that half in there, you end up with a 1/5 mv squared over here. You end up with this, 1/2 mv squared plus 1/5 mv squared. Once you plug all this stuff in, you get that. And then you can plug your numbers in. All right, part B. Okay, calculate the magnitude of the sphere's velocity just as it leaves the top of the incline. So here you go, here it is, rolling, 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 taking off. Woo. What velocity does it leave?
I'm going to do conservation method.
There's no friction.
There is friction,
But it does no work.
but it's rolling without slipping, so there's no work done.
Okay.
Okay, so we get the kinetic energy total here
Yes.
equals
The gravitational potential.
gravitational potential plus its kinetic energy total over here.
Yeah.
Okay?
And it has both
So,
sides.
if you work that out, we already have 1750 joules on the left side. On the right side, we're going to have an mgh plus a 1/2 mv squared plus a 1/2 I omega squared. Now the 1/2 I omega squared, once you do the substitution for moment of inertia and v squared over r squared, this becomes a 1/5 mv squared once all the cancellation occurs. Now notice, because we already have this number over here, we cannot just cancel out m. So some students may want to rework the whole thing. That's up to you. Can you pretty please what? So this is what, 7/10? Can you pretty please use 10 as your g? And the answer comes out easier? So you just have to plug in your values here. Mass of, what was our mass? 25, 9.8, height of 3, plus 7/10, 25, v squared, 1750. V equals. Anyone?
Good.
Yeah.
I think you messed up on,
Yeah,
the second one said, it says 1/5, it's 3.5,
no, it's supposed to say one
it's
fifth.
1/5 because it's 1/30 times.
Okay. Right here, this becomes 2/5 m r squared, and this is v squared over r squared. The r squareds go away, and the 2 cancels that 2, and you end up with 1/5.
Oh, okay.
I've transformed this into this. Okay, so these are the same thing.
I got 7.6.
I got 7.6. Yay, team. We will assume that we are correct. All right, now, number 2. Specify the direction of the sphere's velocity just as it leaves the top of the incline.
25 degrees, another result.
Now, why is that an important question to ask?
I can't.
It seems like, well, doesn't that just make good sense? But this is an energy problem that we just solved. Energy's a scalar. So technically, we don't know what direction it's going, right? Now, the only way we know what direction it's going is that, well, it leaves at 25 degrees, right? Okay, that's actually a very valid question to ask, because, like for instance, if we have a ball and launch it up at an angle, and then we say somewhere over here when it's a height h off the ground, what's its velocity? We can find that with energy, but we will not know the direction, right? We can find the magnitude, but not direction, because that's a scalar. To find direction, we'd have to use kinematics, right? So there are some limitations to energy to be aware of. The limitation of this is we don't really know the direction. The direction is 25 degrees. Okay, part C. Oh my goodness, it's a trajectory motion problem.
What a coincidence.
What a coincidence. I'll let you solve that at your leisure.
Yeah,
Yes, ma'am.
What if we forgot to?
everything has better if you put some word after to it.
You did it wrong.
Okay, so my sister told me this yesterday.
Oh, no. Part 1 just asked what's the magnitude of the sphere's velocity. Part 2 asked for the direction.
Saying bacon.
25 degrees. It's just the same direction as the incline.
Isn't that